All right. Hello, everybody. Welcome back to Comp 3430 Operating Systems. I hope that you're all doing okay. I hope that you are staying cool. It is so hot outside. It is so hot outside. I talked way too much about the weather last term, and I just can't help myself. I don't know. I like to think that this is a Winnipeg thing. You know, you live here, and thus you must complain about the weather, no matter what the weather is. But it might just be a Franklin thing, complaining about the weather all the time. It was a pretty the bike ride home yesterday was it was okay, I guess, question mark. Like it was okay. The wind was pushing me, but every time I would stop, every single time I would stop, it would just be like instantly sweating. Yeah. And so I look forward to the same thing today. I hope that you're all doing all right today. What I want us to talk about today is kind of what I had planned for us to talk about yesterday. So to briefly remind you of what I said at the beginning of yesterday's class, today my goal is for us to take a look at vsfs and ext2. What I want to do with this is, in terms of describe the data structures that are used to represent files and directories as seen on Unix, describe how a specific file system is implemented, and show how common file operations are performed in terms of scratch off manipulating here and just say reading data structures that are in a file system like this. My goal for today is to take a look at a specific property of vsfs. The really specific thing I want to call to your attention is this idea of indirect blocks. This is something that I put in the video, but is not actually in the chapter. So I want to dwell on this for just a moment to give a better idea of what the idea of indirect block pointers is with vsfs. Then what I want to do is I want to move on to doing something a little bit more practical with ext2. So as I mentioned last class, vsfs and ext2 are so close to each other that I'm just going to call them the same thing. There are certain things in ext2 that don't exist in vsfs, and we're just going to ignore that they're there. We have to know that they're there for today's exercise, but we don't have to care too much about them in terms of file systems overall. We're going to use some tools to work through a file system in a text editor. Something that's called hexdump is the tool that we're going to be using to manipulate, to move through the file system's data structures. And then we're going to move on to taking a look at how to do stuff like this with C. So first things first, just a quick reminder here. vsfs is the very simple file system. This is the file system that's described in our textbook. And I'm actually going to pop open this diagram and take a little bit of a closer look at it to remind you of what the overall structure of this is. The diagram at the top here, this is our high-level volume overview. When we did this with exfat, this is where we were doing things like drawing the main boot sector at the very beginning, drawing the extended boot region, the backup boot region, the FAT, and then the cluster heap. In terms of the similarities between exfat and vsfs here, there are structures that we know about in exfat that exist in this volume structure as well. So the super block here is metadata about our file system. We discovered that last class, or thought about that last class when we were looking at Mentimeter. Then there are two bitmap structures, and I'll talk a little bit more about those bitmap structures in a moment. There's the inode bitmap and the data bitmap. These are generally called allocation structures, and they represent use or not use, free or not free. They represent whether something has been used or not used in the rest of the file system. exfat does have an allocation structure. As you're going through the root directory, one of the directory entries that you might notice in the root directory is the allocation bitmap. This is a data structure that is an allocation structure, and in exfat, the allocation bitmap refers to the clusters in the cluster heap. This is the allocation structure for that. Following the inode bitmap and the data bitmap, in vsfs, we have this inode structure. The closest synonym to inodes in exfat are entry sets. Not just one directory entry, but the entire entry set for a file is the closest thing that we have as a synonym for an inode in exfat. but the inodes themselves now represent files. So one inode represents one file, one inode represents one directory, in the same way that we have entry sets for both files and directories in exFAT. After the inode region here, we've got the data region, and this is the same thing as the cluster heap in exFAT. One of the great things about this file system and ext2 is that everything is a block. Everything is a block. We don't have sectors in some places and clusters in other places. In vsfs and ext2, everything is a block. So the super block is an entire block. The inode bitmap is one or more blocks. The data bitmap is one or more blocks. The inode region is more than one block. And then the data region is measured in blocks. Everything is blocks here. So we have the same consistent sizing for everything in this file system. vsfs is remarkably similar to ext2. And like I said, ext2 here is a for realsies file system. This is the file system that was used by default on many Linux distributions for quite a long time. This is an actual file system that is for real. I really specifically want to take a look at this idea of direct and indirect block pointers in inodes. And I'm going to take something that looks like this diagram here and kind of mark it up to give us an idea of overall what that structure looks like. So I'm going to pop over here to my tablet, and here's the diagram that I've started with here. That's kind of like the high-level volume overview of what we have in vsfs. And I've tried to mark up some of this stuff to begin with. So the idea that blocks are approximately the same thing as clusters, this is true. It's something that's usually one or more sectors. It's usually bigger than a sector. Block size is generally 4 kilobytes. Generally, it's not universally 4 kilobytes, but it's generally 4 kilobytes in the same way that cluster sizes are generally 4 kilobytes. We've got this inode region and the inode region themselves. Each of these are going to be sized structures. So every inode that's in our inode table will take up some number of bytes. When we go through the process of working with the ext2 file system today, we're going to specify that our inodes have 128 bytes in size. But unlike directory entries, one inode contains all the metadata for a file. So we don't have many different inodes for one file. One single inode contains everything for one file. I want to quickly take a look at this idea of a bitmap here. So I guess I'll quickly ask, just by show of hands, how many of you have seen this term before outside of the context of Microsoft Paint? Anybody? One person? Okay, so awesome. I'm going to dwell on this for a moment. So this bitmap structure here represents the use or not use of part of our file system. So use or free. The bitmap structure here is bits. It's a big bag of bits where each bit's location represents some other location or some other structure in the file system. So the inode bitmap here is a bitmap that's describing which inodes are free in the inode table and which inodes have been used in the inode table. For the sake of our discussion, I'm going to draw inodes out a little bit like this. I'm going to say that inodes kind of fit on the grid of what we've got here. And our inodes are numbered. Inodes are numbered starting at 1. Sort of like how the cluster heap starts at 2, except I believe that this is a sane choice. 1 is a good starting point for an array. 1 is a fine starting point for an array. It's not 0, but it's also not 2. So our inodes are numbered. And the structure that we're going to have here is that this is going to be a very long array of bits up to our block size. And each of these spots here is going to be one single bit. So this is a 1 or a 0. Bit 0 here, the very first bit in this array, is going to represent whether or not inode 0 has been used. There is no inode 0, so we're just going to ignore that one. Bit 1 here represents whether or not inode 1 has been used or not used. Bit 2 represents whether or not inode 2 has been used or not used. 3, 4, 5, 6, 7, 8, 9, and so on. Every bit in this structure, the indexed bit corresponds to the inode in the inode table, the same numbered inode in the inode table. And the value that we have here as a bit, we're going to say that inode 1 is not currently used, inode 2 is used, inode 3 is used, and the remainder of the inodes in this structure are not currently used. So that means that we're going to have something like inode 2 has been populated, inode 3 has been populated, but the remaining inodes are free. When I'm going through the process now of trying to find a place to put a new file, in this file system, the first step is that I'm going to have to make a new inode to represent this file. With exfat, when I wanted to make a new file or folder inside of an existing file or folder, so either the root directory or some other directory that's on the system, I had to add new entry set for that file into the directory. So I had to add a file, I had to add a stream extension, and then I had to add one or more file name directory entries to that directory. With vsfs and ext2, the first step here is I need to add metadata for that. And so the approach that I'm going to use for this is step 1, look at the allocation structure to find a free inode. So find out which inode in this structure in this table has not been allocated for use by any other file or directory. And the way that I'm going to do that very quickly is just by scanning this bitmap. Find the first entry here or use some other mechanism to find an entry that is marked as 0. This is not currently used. Once I've done that, then I can go to the inode table and I can start populating this with metadata about the file that I'm about to put into this file system. So I can start adding information about the file that I'm going to put into this thing. Our inode structure, I'll come to you in just a second. Our inode structure here, again, just a quick reminder, inodes each inode corresponds to one file or folder. Yeah. So that's the difference between vsfs and ext2. The presence or absence of entry 0 is a little bit irrelevant in terms of what we're thinking about with file systems, in the same way that the off by 2 arithmetic for the cluster heap is also kind of irrelevant in the context of like thinking about file systems. When we're actually implementing file systems, it suddenly becomes very important. But when we're just thinking about file systems, the presence or absence it's not that important. But thank you for raising that point. Any other questions about this idea of a bitmap so far? We okay with this? Okay, awesome. All right. So that's the idea of a bitmap. And then each inode that we have in this inode structure is going to represent an individual file. So I'm going to zoom down here a little bit. And what I've got here is this picture that I've drawn of my cat, Walter. Walter, for the record, loves hot days. He really, really loves hot days. Yesterday, he was... I like to describe this. This is how we describe this idea in my house. When Walter goes outside on the hot days and the patio is nice and warm, he just lays down. But Walter has this tiny tummy that sticks out and it kind of flops underneath him when he runs. And so it kind of starts to look like there's this furry puddle on the ground. And I'd like to say that he's melted into the ground. So here's my picture of Walter. I'm going to add the saggy little belly here that flops back and forth as he runs around. The inode itself is going to have metadata about our file. And so I'm going to put, this is almost equal to an entry set. This is approximately the same idea as an entry set in exfat. The metadata about our file in vsfs and ext2 includes things like mode. This is the word that's used in the file system itself, but this is another word for permissions. So permissions are going to be things like whether you can read, write, or execute the file. Permissions on files in Unix file systems are for 3 different sets of users. There's going to be permissions for the user who created it. That's going to be represented in the metadata for the file as the user ID. The user account that actually created this thing, or the user account that owns the file. It's not necessarily the one that created it, but it's the one that currently owns it. The metadata here is also going to have the same kind of things that you're seeing in the directory entries in exfat. So how many bytes this file has in it right now. vsfs and ext2, unlike exfat and the entire fat family of file systems, they don't separate how to find the data from the metadata itself. So with fat, with exfat, the fat itself is a separate structure. This is how we're going to be able to find all the clusters for a directory or all the clusters for a file in my file system. With the inode structure here, we've mixed that in. We have a set of direct block pointers. And this is going to be some fixed number of pointers that refer to the blocks where the data for this file actually is. This is described in ext2 as there are 15 direct block pointers. How many there actually are is irrelevant, but this is an array, and the array here says this is which block actually has the first bit of data for this thing. So I'm going to say up here that in my data region, n is equal to 17, and the first block for walter.bmp is going to be 17. The second direct block pointer for this will be, let's say that it's 19. And so Walter here is spread across 2 different blocks. Walter.bmp is a pretty small file. The fact that it takes up 2 blocks, so it's more than 4 kilobytes, is surprising, but I wanted to make a hyper-detailed picture of Walter. Our direct block pointers here are going to be, these are exactly the place where you can find the data for this thing. Inodes themselves can also have indirect block pointers. Typically, there's 1 indirect block pointer in an inode. This isn't necessarily a universal truth, but typically there is exactly 1 indirect block pointer. And the indirect block pointer is going to be used after all direct block pointers have been used. So after all the direct block pointers have been filled for a file, then I'm going to spill over into this indirect block pointer structure. My indirect block pointer is going to point at a block. So I'm going to say that this is going to point at block number 20 for our illustration here. And what we're going to find in block number 20 is a series of block pointers. So I'm going to say that the next data for this file is going to be at block 21, and then block 22, and then block 23, and then ... This is a block filled with block pointers. So if our block size is 4096 bytes, if it's 4K, then our direct block pointers are going to be able to represent or refer to 15 times 4 kilobytes of data, which is, I don't know, I can't do that arithmetic in my head, 50 kilobytes, 60, something quite small, something pretty small. I'm doing a bad job of arithmetic here. It's like 400, 500 kilobytes. That's about where it ends. Once we exceed that, then we're going to go to our indirect block pointer. Our indirect block pointer here is going to be an entire 4 kilobyte size block. And if each of these block pointers are 4 bytes in size, and it's full of block pointers, that's a lot of data that we can refer to now. So the idea of an indirect block pointer here is once you've exhausted the space in the inode for the direct block pointers, you just fill a block with more data. And now this is a little bit like where we're going back to the FAT. We're going to a different location on the disk to be able to find information about that thing. There can also be doubly indirect and triply indirect block pointers, where we have doubly indirect block pointers are a pointer to a block that's filled with doubly indirect block pointers, and each of those are referring to direct block pointers. And then triply indirect is to doubly indirect, to singly indirect, to direct. And the file size can explode here. Yeah. Can you repeat your question, please?
So let's say the US has 4
Yeah.
For the inode swap, if we know that this is an indirect pointer.
Yes.
Let's say there is doubly indirect pointer. How will the OS know that that is not the data, but that is an indirect pointer?
So the way that this is going to work is that the inode itself will have doubly indirect pointer as a property, and it may have triply indirect pointer as a property. And then it knows that the first level of indirection is meant to be double indirect pointers or single indirect pointers because it's followed that path. Yeah, so I'm sorry, I omitted this for brevity, but yeah, the idea is that the operating system knows because it's followed that specific thing from the inode itself. Yeah, yeah, good question, thank you. Yeah.
So basically that direct block pointers is what the actual data is. Like you can go with first block, which is 17,
Yep.
which contains data,
Yep.
and so on and so forth. Now, when you go to the indirect block pointers, I'm a little confused on what that means. Just contain more data somehow.
So the first indirect, the only indirect block pointer that we have in our inode here says that block number 20 is going to be filled with more direct block pointers. So what we would then find here at block number 21, so that's this one up here. Let's say that I made this picture of Walter much, much, much bigger. Block number 21 then would be the picture of the sun on a hot day making Walter melt into the patio. So my indirect block pointers here says follow this to block number 20, and then the very first 4 bytes or whatever in block number 20 is another block pointer. And if you follow that, it's data. That's right, exactly. This is an array of block pointers in block 20 itself. So the first little array is in the inode structure, in the inode table, and then if it gets bigger than what we can represent in that, then we have to move it to a block itself. Any other questions about this? We're all okay? All right. Okay. So this idea of indirection here is going to come back to us later, but not when we're thinking about file systems anymore. This idea of indirection is going to come back to us later when we're starting to think about virtual memory and how an operating system works together with the hardware to manage physical memory. And one of the ideas that we're going to find with that is that this idea of an indirect block pointer in our file system is directly synonymous with another structure for managing virtual memory. And the idea is effectively the same. We're going to break up memory in such a way that ultimately it looks like a file system, and we're going to have these things that look like indirect block pointers when we're doing this structure. But for now, what we've got is indirect block pointers with our file system. exfat does not have a synonym for this idea of indirect block pointers. exfat and the fat family of file systems, it's the fat, and that's it. Yeah. So the question is there a case where you don't fill up the direct block pointers first? And no, the strategy will always be to fill up the direct block pointers first, yeah. And part of this is for efficiency's sake. If most of the files in my file system are smaller than what can be addressed by the direct block pointers, for me to find all the data for that file, I just have to load the inode from the inode table. And this is an important difference between this inode-based file system and exfat. With exfat, to find all the data for a file, I have to go to the fat, unless it says no fat chain. But I otherwise have to go to the fat. With small files here, I can just go to the inode, pull the inode out, and immediately have access to at least the first 16 or 15 blocks worth of data. Yeah. Yeah.
So that would mean that in exfat, file storage would be consistent because there are no indirect block pointers in the file either. But if different in this, because we have indirect block pointers, we can add more block pointers to the file.
Well, okay, so the number of blocks that we can point at here is very big, but the number of clusters that you can have in a cluster chain is also very big. It's also very, very big. We can actually very quickly take a look here at the ext2 wiki entry, and one of the properties that it has here is things like what's the maximum file size here. The maximum file size here is a property that is defined by the number of direct block pointers, the number of indirect block pointers, and thus the number of reachable blocks that have, and then doubly indirect and triply indirect, and thus the total number of blocks that we can reach. The size here is between 16 gigabytes and 2 terabytes because we can change the block size of the file system when we're creating it. With exfat, and I didn't plan this before, so I'm not actually sure if it's going to say it here. Usually does. The max file size here is 128 petabytes, which is big. Yeah, it's really, really big. This is going to be a property of how big of a file can you put into the size of the file, and if you set it with a no fat chain property, what's the biggest file you can have? And if I'm remembering correctly, the the file size property is 32 bits. I don't remember. It might be 64 bits. It might be 64 bits, but there's a property of that. Yeah. Yeah. All right. Okay, cool. So I want to take a look at a real file system now. And the real file system that I want to take a look at is actually ext2. Some of the ideas that I'm bringing to you about vsfs are kind of like me pulling stuff in from ext2 but generally it's consistent with the idea of what vsfs is. I want to take a look at a real file system, and I want to look at it in a couple of different ways. The first is I want to make a file. So kind of like what we're doing with our assignment, we can't really work with hard drives here. That would be a little bit outside the scope of this course to start building device drivers for us. So I want to work with a file. I want to format this file using the ext2 file system, and then I want to inspect it and find certain data structures using a program that's called hexdump. Hexdump is a tool that we can use to take a look at binary files or any kind of file really, but it will show us the contents of the file in a hex format. So we can start to navigate around our file system like that. Once we spend a little bit of time with that, the other idea that I want to do with this is I want to spend some time writing some code in C to be able to do approximately the same kinds of things as what we're doing with hexdump. So finding data structures in this file system and kind of working our way around the file system. I encourage you to follow along with what we're doing. And I've put everything that you need to start with up on this repository on GitLab. This is something that you're going to need to have a Linux machine for. So if you've got a local Linux environment, great. If you want to use Aviary, that would be another place that you can follow along with this. So I'm going to pop over to my terminal here, and I'm going to start by cloning this repository. ext2-inspect. I'm going to change into this directory. And there's a few different things here. I've got a skeleton program that will give us a starting point. What's in the skeleton program in the C program right now is a set of predefined structures so that we don't have to spend a bunch of time building up the structures that we're going to be using for this. There's a make file. There's a README that describes some of the stuff that I'm going to do with you verbally, so I'm not going to open the README itself. And then there's a directory here that's called ext2 files. The contents of ext2 files is another README file, and the content of this README is this. It's not very much. It's quite a small file, but I just want to have a file that we can put onto the volume so that we can find the file in the volume using this tool hexdump to be able to work through the file system. The very first thing that I want to do here is I want to make an empty file that I can start to put my file system on. The program that I'm going to use to do this is called truncate. Truncate is a program that will just make an empty file of a specified size. It doesn't put anything in it. It might be filled with zeros. I actually don't know. I've never looked at it after I've done truncate. It makes a file of a specified size. I want to make a file of a specified size, and I want this to be quite a small file. So I'm going to make this a 256 kilobyte size file. That's the size of the file system that we're going to use here. This is pretty small. This is smaller than like the smallest floppy disks, but it is small so that we can start to actually take a look at the content of this thing. I'm going to call this file that I'm making ext2 volume. I'm going to hit enter on my keyboard. And what I'm going to have now, if I do ls-lh, is I've got this ext2 volume file here that takes up 256 kilobytes. And if I take a look at the contents of this file right now, I'm going to use hexdump. I'm going to pass -C. Uppercase C says I want this to be in canonical format. This is going to print out a nice table, and then it will print out beside the table an ASCII representation of everything that's in that table. I also want to pass -v. Lowercase v says verbose. By default, hexdump will skip lines that are just 0. Rather than printing out a bunch of zeros, it just skips it for you. But I actually want to see those lines. I'm going to do ext2 volume, the name of the file that we just created. And I'm going to hit enter on my keyboard. And it appears to be filled with zeros. There's too much data for me to actually see on a single screen here. So I'm going to pipe this into a program that's called less Less is a pager, and it's going to allow me to kind of like move up and down within the file in my terminal here. So within less, if I move down by pages, so I'm hitting page down on my keyboard, truncate fills this file with zeros, which is good. That's kind of what I want to see for now. I'm going to hit Q to get out of less. Once I've made this file, I want to actually put a volume on it. I want to write an ext2 file system to this volume or to this file. On Linux systems, this is often of the form mkfs, so make file system. And then often you can say dot and then the name of the file system that you want to make. This may differ based on the system that you're on, but this should be the same on Aviary. This is Ubuntu that I'm running. If you're running Ubuntu, it should be the same command that you're using. I'm going to say makefs.ex2. There are some options that I can pass to makefs to manipulate the structure of the file system or to set some properties of the file system when it's creating the volume in the first place. The first one is this -d option. -d says, I want you to take what's in the directory that I'm going to pass to you and put it in the root directory of the volume that you create. So I want to take ext2 files here, the contents of this directory, and I want to put that README in the root directory when the volume is made in the first place. So I want to drop some files in this thing as soon as it's made. I want to put a label on this volume. So I'm going to say -L. The label here is kind of like, you know when you plug a USB drive into your computer and it shows up and it says this name has been attached? That's the label that we're talking about here. So the label in ext2 is going to go into the superblock itself. With exfat, the label goes into the root directory as one of those directory entries. I don't really know why. I don't understand why it's not in the main boot sector, because there's lots of space in the main boot sector to put something like that, but it's in the root directory at exfat. In ext2, it's put into the superblock. The label that I'm going to put onto this is comp3430, and I want to put S25 here. So summer 25, comp3430. The next thing I want to change here is the size of our inode structure. So I'm going to say -I. These are options right now that I'm setting that are fixed. Once I make the volume, we cannot change these sizes. I can't change the size of an inode after I've made the volume. And part of that is the inode table is fixed in size. We're going to have exactly a certain number of inodes, and because they're all the same size, there's exactly this many inodes in the inode table. I want my inodes to be 128 bytes in size, so I'm going to say 128 here. And then the last thing I have to pass to this is the name of the file itself, so ext2 volume. Normally when you do this, you're going to pass like a /dev/ something else if you were doing this for real on an actual drive, but we don't have permission to do that on Aviary, and I wouldn't want to mess up any of your drives, so we're just going to do it on a file. I want to point out one thing here. 128-byte inodes cannot handle dates beyond 2038 and are deprecated. So I'm making these smaller on purpose just for us for this example. But with 128-byte inodes, all of the date fields that are in the inode, and we can take a quick look at this, but all the different date fields that are on an inode have to be compressed a little bit. They have to be made smaller so that they fit into 128 bytes. In practice, when you make an ext2 formatted file system, inodes are 256 bytes in size, so they're quite a lot bigger, and you can put more. You can allocate more memory for the dates that are there. So what this has done is it's made a file system. It's got 64 blocks, and it's got 32 total inodes here. Now what I want to do is I want to start taking a look at the actual file system itself. And so I'm going to use that hexdump command again. Hexdump -C, ~C for canonical format, -V to don't skip 0 lines, the name of the file, and I'm going to pipe that into less. And I'm going to hit enter on my keyboard. And we got a bunch of zeros here. We still have a bunch of zeros here. What's the deal with that? That's maybe not quite what we were expecting. I'm going to go to my web browser. And I put this link into the lecture notes for today's lecture. I want to take a look at this document here. This is the second extended file system internal layout by Dave Poirier. And this describes the whole overview of ext2. This describes the overview of ext2 as a structure. I'm going to go directly to the superblock here, but to give you a mental image of this, we do have a superblock. It is very close to the beginning of the file system's volume. That's the first block that we have, and that's sort of consistent with vsfs, except as we can see, it doesn't actually start at the beginning. This is not at offset 0 that we're looking at here. After the superblock, what we've got is going to be a set of block groups. This is a difference between vsfs and ext2. We're going to step through it for this example, but we don't really need to know or care about block groups. We can just assume that we've got an inode table. And when I do take a look at this block groups idea, the block groups themselves, if I scroll down just a little bit here, this block group descriptor table itself refers to an inode table. And so we're going to be able to find an inode table in this file system. The inode table itself is going to refer to inodes, and then the actual data is going to be in the data region of this file system. So I'm going to click on the superblock here. This is the disk organization, and it describes the structure of the file system that we've got. And the very first sentence here says, the superblock is always located at byte offset 1024 from the beginning of the file. So that explains why, at least initially, what we're seeing here is a bunch of zeros. There isn't actually any data at the very beginning of the offset of the file, so it's somewhere else at offset 1024. I don't know about you, but I can't go back and forth between decimal and hexadecimal very quickly. But I want to be able to use hexadecimal because these values here, this column is the offset into the file, but it is in hexadecimal format. What I like to do with this is I like to have my calculator open. My calculator has like switch back and forth between decimal and hexadecimal mode. I think the Windows calculator can do this, I think. Does anybody have Windows open right now? Can you switch to like a programmer mode in the Windows calculator? You can. Okay, awesome. So today I learned you can do this in the Windows calculator, and I'm not sure about Mac OS. If anybody wants to check that, I welcome you to. It doesn't? Oh, it does. Okay, so every calculator we have can do this. Great. Thank you, calculator makers. I want to go to offset 1024. And offset 1024, I realize this is quite small, so I'm going to read it for you. 1024 is 400 in base 16 in hexadecimal. So in less, I can search for a string by hitting /, and I'm going to type in 400 to find the line that has this on it. And okay, all right, there's some data here. Good. So we've gone 1,024 bytes or a kilobyte into the file, and now we're able to start to see some of the superblock for this file. The beginning part of this is inscrutable. However, I will draw your attention right here. That's the label. That's the label that we put onto this file system. So the label here is at some offset, comp 3430-S25, and it's taking these values here, these hex values here, and it's printing them out as ASCII here. This is that -C option on hexdump to be able to do this. So we're at the first kilobyte of the file. What I want to do is I'm going to be switching back and forth between this documentation to kind of like make connections between the superblock structure and the other structures that we're looking at and the data that we're looking at. This table here shows us that the first thing in the super block is the total number of inodes that were in this file system. And the second 4 bytes show us the number of blocks that are in this file system. So if I go back over here, the first thing that we're going to see is that the first 4 bytes here represent the total number of inodes in the system, and the second 4 bytes here represent the total number of blocks in the system. I'm going to have to go back to my calculator, and I'm going to switch to hexadecimal mode. And the value that we have for the first 4 bytes here is 20, and that says that there are 32 total inodes in the system, which is consistent with what we saw as the output from makefs.ext2. And there are 40 blocks, so there's 64 total blocks in this file system. The output with hexdump here is kind of like backwards looking. This is little endian output. And so the smallest or the least significant part of our number is being presented here first, and then we're kind of reading it backwards like that. So the first 4 bytes here represent the number 20, and the next 4 bytes here represent the number 40. When we're working with this data in C, we don't care. We don't have to care about this. It's just going to happen automatically for us. When I read 4 bytes from this file system, it will load it in the correct order into the variable that I'm working with, so that I don't have to like do byte shifting to be able to reverse the order of the bytes that I've got here. This is an artifact of hexdump printing it out in little endian formats and not reversing it for us. So we've got the total number of inodes, and we've got the total number of blocks, and we can also see in the metadata for the file system the label that we have for this thing. The place that I want to start to go is I want to start looking for the inode table in this system. Unlike exfat, this file system does not tell us where the inode table is in the superblock. So there's a lot of properties that are in the superblock, but none of these tell us where the inode table is. To do that, I'm going to go back to the top of this file, and I'm going to go down to the block group descriptor table. The block group descriptor table is described here as it starts on the first block following the superblock. So when we made this file system, we made this file system with 4 kilobyte sized blocks. The blocks here are 4096K. The super block for us is at block 0. It's pushed to 1 kilobyte into the file, but it's still fully contained within that first block. And so this block group descriptor table is going to be located at an offset of 4096. That's the first block after the super block. So I'm going to pop over to my terminal here, and I'm going to type my calculator. I'm going to type in 4096 in bytes in decimal. And one thing that's pretty convenient about going back and forth between hex and decimal with numbers like 4096 is that this is conveniently 1000. And this is also going to be convenient for us later when we're thinking about block numbers, because the block number is just going to be that hex number prefixing 000. So I'm going to go now to location 4096, which is at offset 1000 in hex. At offset 1000 in hex, what we're now starting to take a look at is the block group descriptor table for this file system. I'm going to go back to the documentation here. And what we see is the first byte here is the block bitmap. This is that allocation structure where we would go to that block and start counting the bits, or start finding a free block by looking for a 0 in the bitmap itself. The second 4 bytes represents which block is the inode bitmap. And so that's where we go to find out which inodes are currently in use and which inodes are not currently in use. The next 4 bytes here represents the inode table itself. This is the block that's representing the inode table. So I'm going to go back to my terminal. Our first 4 bytes here is one of the allocation structures. And what this says is that that's going to be at block 2. The next one is block 3. And this one here is our inode structure. And this is block 4. Block 4 is, again, conveniently 4 times the block size. And so I don't have to do this in my calculator. This is just going to be offset 4,000 into our file, so hex 4,000. And this structure here now is the inode table itself. The inode table itself is filled with inodes. This is where we're going to find all the metadata about the files themselves. The metadata about our files includes lots of stuff. And I'm going to pop back over to my documentation here, and I'm going to click on the inode table, and I'm going to click on inode table here. And here's where we can start to see things like the mode, the user ID. So the first part is the permissions. The second part is going to be who owns this file right now. This part is going to be how big the file is, so how many bytes are in this file. And then ultimately what we're going to see down here is the block pointers. These are the direct block pointers for this file. With ext2, the way that the indirect block pointer works is that it's the last entry in the set of direct block pointers. So there's just one array that's block pointers, and then the last 1, 2, or 3 of them have special meaning that say this is the one that you'd follow to find those indirect type of block pointers. I'm going to go back down here just a little bit, and I want to show you this table 3.14. And what this says is there are inodes that have special meanings here. The first inode, so this is inode number 1. This is something that's called the bad blocks inode. This is going to be the inode that refers to blocks in the data region that should not be used for files, because when the hard drive tried to read a sector from that, it reported that it was unable to read it. This is a part of the drive that's starting to go bad, and you shouldn't try to use it for anything. Inode number 2 is the root directory inode. That's the one that we care about. That's actually the one that we care about here. In exfat, you have to use the main boot record to find out what the first cluster of the root directory is. In ext2, the root directory is always inode 2. It's always inode 2. This is a fixed value. It's never going to be some other property. It will always be the second inode in the table. And so I'm going to go back to my terminal here. And what we're going to look at here is at offset 4,000 into the file. This is block number 4 that we're looking at here, the start of our inode table. Every inode is going to be 128 total bytes in size. Inode number 1 is the one that's at offset 4,000 here. So remember, this is not a 0-based array. This is a 1-based array. Inode number 1 is the very first thing that we're finding in this inode table. 128 bytes in hex, so 2 decimal here is going to be, to hexadecimal is 80. So between 4,000 and 4080 here, this is inode number 1. Then between 4080 and, now I cannot do this arithmetic in my head. I think it's like 40E0 is going to be the start of the next inode. That's going to be the inode that represents the root directory in this system. What we've got at the very beginning here, and I'm going to go back to the inode description here, is that the first 2 bytes here represent the permissions. So these are the permissions for the root directory on this system. I'm going to go back to my table. The next 2 bytes here represent the user ID that owns this directory. So these 2 bytes represent the user that owns the root directory on this volume. On a Linux and Unix system, typically the user that has ID 0 is the root user or the administrative user of that system. So nobody else is going to be able to put stuff into that location in the file system. Then there are many other things. And the one that I want to get to here is I want to start being able to ask questions about the contents of the root directory itself. And so this is at byte offset 40 in the file is where we're going to find the array that represents the direct block pointers for this thing. This is going to take us down to this row right here, and this is the first direct block pointer for the root directory, and this is the only direct block pointer for the root directory in this system. This says that the contents of the root directory are located at block number 5 in this file system. So I'm going to hit / and I'm going to go to 5,000 here. Block number 5 is a multiple of that 4096. And we got some stuff here. We can see two things right away. The first thing that we can see is this thing that's called lost and found. And then we can see the name of the file that we put into this volume when we created this file system in the first place. This is that readme.md. This is the thing that was inside that directory that we passed with -d. What we've got here are directory entries for this file system for the root directory. The directory entries here are limited quite a lot more compared to what we're thinking about with directory entries for exFAT. The directory entries that we have in the ext2 file system, and I'm just going to scroll down here a little bit because it's right beneath us, underneath all the description of the properties that we have for this. The directory structure. The directory entries here are limited to what inode has the data for this file, or the metadata for this file. How long is the directory entry itself? That's this record length thing. How many characters are in the name? Is this a directory or a regular file? And what is the name of this file? That's it for directory entries for this thing. So what we've got in our file system here is at the very beginning, we've got inode 2. That's the first directory entry in this directory. Inode 2. After that, 4 bytes is the record length. So this says that this record is 0c bytes long. Then what we have after that is 1 byte for the name length. The name is 1 byte long. After that, we've got the file type. 2 here represents this is a directory. So the first thing that's in the root directory is a directory. And then what immediately follows that file type is the name. The name here is 1 character long, and it's the hex value 2e. The hex character 2e is, unfortunately for the output of hexdump, a dot. When I do ls-al, when I do, I'm going to change into this example directory, lecture 6 ext2 inspect. When I do ls-al, what I see is there is a dot. There actually is a dot. The dot here says this is a link to the current directory. And that's why the inode here is number 2. It's a self-reference back to the root directory. After that, we have the start of another inode, or another directory entry, sorry. It points to inode number 2. It has 0c bytes for record length. It has 2 characters in its file name. It's a folder, and it has ... Look at that. It's the ... The parent directory of the root directory is the parent directory, so it's also a self-reference. In other folders in your file system, this is going to point to a different inode, but the root directory is special, and so both ... and ... are going to refer back to that directory structure itself. After that, what we've got is going to be this thing that is 0b. So this is the start of this record here, this lost and found. I'll come to you in just a second. The lost and found is a folder, and this is a folder where, we'll talk about this tomorrow, When we're trying to make our file system consistent again, if there's an inode in my inode table that's not in any directory anywhere, it's going to get put into this folder in the root directory. So if there's this inode that's not connected to anything, it will get stuffed into this directory, into this lost and found directory. And the very last part here is my README. And my README here tells me that we've got, this is the end here of lost and found. This is the start of the README. And the README is at inode 0c. And then what we're going to start to find are the characters for README. This is the lowercase d, the lowercase m, the dot, E, M, D, A, E, R. This is readme.md. Yes, yeah. Yeah.
You mentioned that the self-referencing with the dot and the dot dot, the 2D always gets the
That's a dot, yeah. The very first byte here, the very first 4 bytes tells us what inode number that entry in this directory refers to. And so we're looking at the data for inode number 2, which is the root directory on this system. And so the first 4 bytes for those first 2 entries say, these refer to inode number 2. And so it's a self-reference to that inode. And then if you follow that inode back to its data, you're going to get back to the same location. So just to be clear, I guess, our directory entry structure here is that we're looking at the data for a folder right now. And the folder itself is going to have entries where it's going to be the inode number. This is the thing that's inside this directory. And if you want to find the data for that thing, you have to go to this inode. And then we've got the name itself. So this is where we have the dot and dot dot. The self-reference is that the very first entry in the folder for the root directory is a reference back to the root directory's inode. It's just the same number back to the root directory itself. So we're saying that inode number 2 is contained within the directory for inode number 2. Inode number 2. Yeah. Does that clear it up? Okay. Okay. Yeah. So I don't know if I can actually answer that question. The question is, can a file have actually 0 entries in its file name? I personally cannot think of a reason why you would have a file that doesn't have any characters in its file name. And I'm not even sure how you would deal with that with output. I think it's possible, I guess, because the name length can be 0, but I don't know why you would have those entries here. There's no good reason for that to happen in my mind. Yeah.
The inode number supports a file descriptor?
The inode number here is more similar to a cluster number than it is to a file descriptor. A file descriptor is going to be a property that we're going to have in memory. So when we're opening files, we're going to add an entry to an in-memory structure that we have that represents the data for that file that we have right now. And if you were working with inodes in a file system, the inode number might be part of that structure as opposed to being the file descriptor itself. All right. So the thing that I really want to find here is this, readme.md. And if we're scanning through this directory structure here, what we're going to be able to see is that this is at location 0c. This is the inode for this thing. So I'm going to go back to the inode table, and the inode table is at location 4000. This is the start of that inode table. And what we're looking at is inode number C. And inode number C is going to be at an offset. The offset is going to be, and I'm going to write this in decimal, our inodes are 128 bytes in size. I want to go to inode number 12, and I'm going to reduce that by 1 because this is a 1-based array. So I'm going to subtract 1 from this offset that I'm going to. I'm going to add to that the block number that is the start of this thing. And so that's going to be block number 4. And I'm doing this in decimal right now. So I'm going to say times 4096 times 4. Sorry, I want to do 1408 plus 4096 times 4. So that's going to take me to location 4580. In my file. Yes. So this is now the inode for that readme.md. And I'm going to skip past all the metadata that we've got here, and I'm going to go directly to the first block pointer here, which is at 0b. And so that says at block B is the data for this file. And if I go to B1000 now, there it is. We got to the file. We've navigated through this file system in our hex tool to be able to get to the contents of the file that we wrote to the file system when we first created the file system. And we went through this process of going through the inode structure, through this block group descriptor table, and then getting to the point of actually seeing the data for this file. And oh my God, that was tedious. That was really painful. That was awful. That was really, really terrible. Why are we doing this? Why would anybody ever want to do this? Why are we doing this? Just use File Explorer. File Explorer is a good tool. I think I've seen screenshots of it, but I don't think I've ever used it before. But it can. I think it also does like marking it up and stuff too. Like it'll color code stuff. Yeah, I did this in hard mode. I'm sorry. This is really painful, and this is really not the way that you would normally do this. But it does physically take us to these different places in the file system. And while it's difficult for us to read hex, like I'm not going to be spending a lot of time taking a look at the contents here and saying, oh, that's absolutely my README. It is illustrative in the sense that we've moved through this file system to these different structures, and we've used these different structures to be able to get to the point that we want to be able to do. So we should be able to use the data structures or describe the data structures that we're using to get to different locations within this file. That's really painful, and normally I'm going to do this in C, and so I want to start doing this in C. In ext2 and spec.c, what I've got are structures that are partially populated. I didn't go through the process of filling up everything in each of these structures because I don't care about most of the data that's in there. So you're going to see places here where I've done things like I want to skip this. I don't actually care about the content of this. I want to get directly to magic here. I want to get directly to this magic number so that I can inspect it, and I don't care about everything that's in between that. I want to know about things like what's the block size. I want to know about things like how many inodes there are. I've got this block group descriptor table here, and it is fully populated, so it's got everything that we want here. I've got the inode structure, and I've populated this fully. So this is everything that we want to have except for each of the time things. I don't care much about the actual time things themselves. We've got the directory entry structure here, and the directory entry structure here does not have the file name in it at all because I have to treat this separately. Because it's a variable number of bytes that are in these records, I need to do something slightly different. And then we've got our main function here with some initial stuff. So I'm going to start writing some code here that's going to get us through the super block and then start towards finding the directory entries for this file. So I'll leave that void block there. Casting these values to void is a way for me to suppress the warning of this is an unused variable. I can delete this later when I've actually used it, but for now I'm just going to leave them all there because I want to be able to compile this sometimes. So the first thing I want to do with this file system is I want to get to the super block itself. The super block is located at location 1024 bytes or 0x400 in hex. So I can do either lseek FD. So FD is the file descriptor that I got from here from opening it. I can do 1024 and I can say seek set. I want to go to this absolute location, or alternatively, I can say lseek FD, and then I can use that hex value here, 0x400 seek set. So I want to go to the location where the super block starts. Once I'm at the super block, then I can just read the whole super block in. And so I'm going to use read from the file descriptor. I'm going to pass to it the address of the super block. The super block here, I'm going to scroll up for just a second. The super block here is a function scope or a stack allocated variable. So this is not a pointer, so I want to pass the address to this thing. What I want to read from this file at this location is up to size of super block. So this is the type is ext2 super block. Once I've read the super block in, I'm going to do some basic checks. I want to see that I've actually read in an ext2 formatted file system. And the way that I'm going to know about that is if I've got the correct magic number in that property that's called magic. So I want to say if superblock.magic is equal to, I'm going to pop back here in just a second. I'm going to go back to this description. I'm going to go all the way back up to the super block here, and I'm going to click on magic. And this is described as 0xef53. This is a hard-coded value that we know must be this value if this is actually an ext2 formatted file system. So I'm going to say if this is equal to 0xef53, then we are actually working with an ext2 formatted file system. And I'll print out this value. So I'll say printf, the magic number is, I'll say 0x, so that 0x are literals here, %x, new line character, superblock dot magic. I'm going to change to this directory. I'm going to make it. I'm going to run this. I'm going to pass it the volume that we made. And it is an ext2 formatted volume, so awesome. So we're going to proceed with this. The next thing that I want to know is what the block size actually is. The block size is something that we can specify when we're creating the file system. So when we're doing makefs.ext2. I didn't, and the default is for it to be 4096 bytes or 4K bytes for the block size, but we can also calculate this value. The block size is going to be a value that we're calculating from metadata in the super block. And the way that we calculate this is we take 1024 and we shift it to the left by superblock dot log block size. That log block size is a logarithm of the actual value, and so shifting 1024 by that much is going to give us the block size of the thing that we want. This idea is similar to the sector size shift. I forget the exact property name here. The sector size shift in exfat. And the idea with exfat is that you're going to do one left shift sector size shift to be able to do that. You can use POW if you want from the math library, but doing this shift by one is also a way to accomplish that. So the block size here, I'm going to make this one more time, and I'm going to run it. And the block size is 4096 bytes. And then what I'm going to do is I'm going to finish this tomorrow because it's already 1:44, and I've wasted so many extra minutes of your time that I don't want to do that anymore. But what I'm going to say is this: we will finish this part tomorrow. And I will also say that if you want to look ahead at what I've done is if you take a look at this Git repository, I've put a branch up here that has the complete version of this ext2 inspect. So if you want to get a sense of where we're going in tomorrow's class at the beginning, you can see the completed part of what I've done for this file, to just so you have a reference of what we're doing here. In tomorrow's class, what we're going to do is spend some time taking a look at inconsistent file systems and trying to repair inconsistent file systems after we do this. But part of that is going to be taking the code that we've got from this exercise and moving into that. So at this point, you should be able to describe the data structures that are used to represent files and directories as seen in Unix. So this is the whole idea now of inodes. This is the idea of blocks. This is the idea of directory entries and that sort of thing. You should be able to describe how a couple of different file systems are implemented, their overall block structure, where different things are, what the different things are, and what those different things do. And at this point, you should also be able to describe how some common file operations are performed in terms of using the data structures. But you should also have a reasonable idea of, if I add a file, I need to use allocation structures to be able to find empty things in the data structures that I've got. That's it for today. I hope that you all have a great rest of your day, and I will see you all tomorrow. Bye, everyone.